Alright, hello class. In this video we're going to continue our discussion of the basic derivative rules. And we'll continue on by basically getting some of the final basic rules out of the way before we start looking at just a bunch of examples and basically build our foundation to build upon. Okay, just to give a reminder of the rules that we've established so far, we have constant multiplication, which just tells us that constants come along for the ride, right? So if you know the derivative of f and you're multiplying it by some constant c, the derivative of the whole thing is just going to be c times f prime of x. Okay, we have the sum rule that if we're taking the derivative of two things added together, we can just do them term by term. We have our product rule, which says that if we're taking the derivative of an f times g, it's going to be f prime of g plus f times g prime. So derivative of the first times the second left alone plus the first function times the derivative of the second function. Okay, quotient rule. Very similar to product rule. In fact, that's how we got the quotient rule. It's the derivative of the top times the bottom minus the top left alone times the derivative of the bottom all over the bottom squared. How I remember this one is just that the top goes first, meaning that I take the derivative of the top first. So it's the first thing that I do, then it's the bottom left alone. Basically same idea as the product rule, just with a minus sign, and then we divide by the denominator squared. Okay? And then finally, we have the power rule, which basically just says that the derivative of x to any power, constant power, p, is going to be p times x to the p minus 1. Okay, and that's, we looked at quite a few examples to show that this is basically true for any power, fractional, positive, negative, whatever. And in fact, even if p is 0, we still get what you might expect, because that would be a constant. And if you have x to the 0, that's essentially the derivative of 1, which is 0, right? We established that. But if we actually apply the power rule to this, you would get 0 times x to the negative 1, which is just going to be 0. Okay, so the power rule even applies for the derivative of constants. All right, so I want to extend this a little bit, or at least show that this is only true for x to a constant power. If we have something to a variable power, it's going to be a bit of a different story. All right, so we have, like I said, the derivative to some constant power is c times x to c minus 1. But what if we instead are looking for the derivative of c to a variable power, right? A constant to the power of x. Okay, what I will say is this is not equal to x times c to the x minus 1. All right, this is not how this works. It would be tempting, but the power rule only holds if you have x to a constant power. If you have a constant to the x power, well, we have a different process we need to follow. Okay, so the most famous form of this would be e to the x. Right, so we want to find the derivative of e to the x. Okay, and so to do that, we'll go to the definition, the limit definition. So the derivative of e to the x will be the limit as h goes to 0, okay, of e to the x plus h minus e to the x all over h. Okay. Now, it may seem like there's nothing we can actually do here. However, if I rewrite this e to the x plus h as this, right, we could write this as e to the x times e to the h, because when you multiply two things to the same base, different powers, you add those exponents. You can rewrite it in this opposite direction. Now we can actually factor out the e to the x from the top, right? They both share an e to the x, and we're taking the limit with respect to x, or sorry, with respect to h, not x, so we can actually take that e to the x all the way out to give us essentially e to the x times the limit as h goes to 0 of e to the h minus 1 all over h. And we need to consider what happens here. Where does this limit go? Okay, so the derivative of e to the x hinges completely on this limit here, where e to the h minus 1 all over h goes. Okay, we can do this using the Squeeze Theorem. There are quite a few ways we could actually do this, but using the Squeeze Theorem, okay, and the fact that the top here, e to the h minus 1, well, e to the h minus 1 is going to be greater than h, and it's going to be less than h times e to the h. Okay, now to show why this is true, we're going to look at a graph. This isn't really a proof necessarily, but I think a graph is actually convincing here. Okay, so here we have a graph. This is e to the x minus 1. This is x, so we can see that e to the x minus 1 is always greater than x. And here's x e to the x. As we can see, that is greater than e to the x minus 1. So e to the x minus 1 is trapped between these two functions for their whole life, but especially close to 0 where we're looking. Okay, so this is true for all h, but specifically close to 0. And so now if we divide everything by h, okay, we'll get, let me write that. Okay, if we divide everything by h, we'll get 1 is less than or equal to e to the h minus 1 all over h, which is less than or equal to, well, h e to the h over h will just be e to the h. And now we can take the limit of all three pieces. So the limit as h goes to 0 of 1 is of course going to be 1. The limit as h goes to 0 of e to the h minus 1 all over h. And the limit as h goes to 0 of e to the h. Well, of course, the limit as h goes to 0 of 1 is 1, right? We'll leave this alone. This is just the limit as h goes to 0 of e to the h minus 1 all over h. And then the limit as h goes to 0 of e to the h, well, that's going to be e to the 0, which is 1. So this tells us that the limit as h goes to 0 of e to the h minus 1 all over h is 1. Oh, well, going back to our previous screen here, okay, we just determined here that the limit as h goes to 0 of e to the h minus 1 all over h, this goes to 1. So this is e to the x times 1, which is just e to the x. So the derivative with respect to x of e to the x is itself. That's interesting. Okay, but if we take a look at just the graph of e to the x and look at the slope of the tangent line as we go across, all right, so here's a graph of e to the x. If we start looking at the tangent line at various points, so here I have the point with its y-coordinate, okay, which comes from e to the x. And now here's the slope of the tangent line, which you'll see is exactly the same as the y value. In fact, as we move this along, you'll see at pretty much every step that we go, we're getting the exact same slope, right? So if we were to chart out the path of the derivative function, we would basically be charting the same exact y value as we have here. So yeah, e to the x, it's the one function out there whose derivative is itself. Right? So derivative e to the x is itself. Is this true for all versions of e to the x? What do I mean by that? Well, is it true for, say, e to the 2x? Or maybe e to the 1/2 x? You know, stuff like that. Is it still true even if it's not exactly x? What about, say, 2 to the x? You know, things of that nature. Well, we'll answer this. It's close. It's not exact. We got e to the x, its derivative being itself, thanks to this limit. We were able to factor out that e to the x from both pieces here, and then left with just e to the h minus 1 all over h. So let's look at something a little more generic, a little more general than this. Okay, let's look at the derivative of e to the rx, where r is a constant. Okay, well, we're going to have a similar starting process, right? We're going to set up our limit definition, so it's going to be the limit as h goes to 0 of e to the x. Well, we're replacing x with x plus h, so this is going to be r times x plus h minus e to the rx all over h. Okay, so this will be the limit as h goes to 0 of e to the rx plus rh, right, when you distribute that, which I'll go ahead and write this as another step. Then, like we did before, this will be the limit as h goes to 0 of e to the rx times e to the rh minus e to the rx. All right, and then we'll have the limit. Well, first of all, like before, now both these terms share an e to the rx, so we can factor those out to get e to the rx times the limit as h goes to 0 of e to the rh minus 1 all over h. So now the question is, does this limit still go to 1 if it's e to the rh here? Okay, so to figure that out, if we go back to what we had here, right, this statement, okay, to isolate that a little bit, this statement, right, is true for all h. Now what I'm going to do is replace every h with r times h. Okay, we can definitely do that. So h I'll replace with r times h, which will be less than or equal to r e to the rh minus 1. There's no h here to replace, and this will be rh e to the rh. This statement should still be true for every h. Okay, and I can show you that on a graph. Okay, so here we are back to a graph. This in the blue is e to the rx. Okay, this in the red is rx times e to the rx. So I'm using x for the graphing, just keep that in mind. And then this in the purple is just the rx, and I've set up a slider to change r to different things, and as you can see, as I slide things around, the blue curve does stay trapped in between the other two. Okay, so no matter what, it may flip things around. So you can actually see their labels now. Okay, so here's the red, the blue, and the purple, and wherever I put this slider, you can still see that the blue graph is trapped between the other two. Okay, so using the squeeze theorem again. Okay, so going back to here, now like before, if these are all trapped together, now we can just divide through by the h to get that r is less than or equal to rh minus 1 all over h, which is less than or equal to r e to the rh. And now we can just take the limit as h goes to 0 of each of these pieces. Okay, and so the limit as h goes to 0 of r, well, there's no h here, so this is just going to go to r. Then the limit as h goes to 0 of r e to the rh, well, this is going to go to r e to the 0, which is r. So this means that the limit as h goes to 0 of e to the rh minus 1 all over h is equal to r by the squeeze theorem. Okay, so now if we step back to our previous work, okay, we got down to the limit, or e to the rx times the limit as h goes to 0 of e to the rh minus 1 all over h, which we just found goes to r. So we end up with e to the rx times r, or specifically, the derivative with respect to x of e to the rx is r e to the rx. So yeah, it's basically itself. So the derivative of e to the x is itself, but that's just because we're using this formula here, because the derivative with respect to x of e to the x, well, we have a 1 here. All right, so that would be 1 e to the 1x, or essentially the derivative with respect to x of e to the x is just itself. Okay, so if we have some other constant, like if we have the derivative with respect to x of, say, e to the 2x, we're going to get 2e to the 2x. Okay, if we have derivative with respect to x of e to the 1/2 x, we're just going to get 1/2 e to the 1/2 x. Okay, so it's the derivative of e to the stuff, as long as it's just a constant times x, is essentially going to be itself times whatever that constant is. Okay, so if you remember this one, you get this one for free, essentially. Now, we're going to have another way that we can describe this later on, all right? But we will get to that when we get there. All right, so that's not something we really have to worry about right this second. Okay. All right, so what about any base that isn't e? Say we have want the derivative of 2 to the x, or 1/2 to the x, or just b to the x for any base b greater than 0. Well, this is actually easier than you might think, because using what we know about natural logs, right, we know that e to the natural log of b is going to be equal to b for any positive b. Right, that's just because e and natural log cancel each other out. Well, if we then raise both sides to the x, right, e to the natural log of b to the x is equal to b to the x, okay, and then whenever you raise a power to a power, you multiply, so really what we have here is e to the natural log of b times x is the same thing as b to the x. And then we can just say, all right, that means the derivative of b to the x is going to be just the derivative of e to the ln of b times x, which, using what we've just talked about, that's going to be ln b times e to the ln b x. And now we can go back to replacing this part with b to the x. Okay, so what that essentially means is that the derivative with respect to x of 2 to the x is the natural log of 2 times 2 to the x. Right, the derivative with respect to x, 1/2 to the x, is, well, it's going to be the natural log of 1/2 times 1/2 to the x. Right, so if you have a base that is not b, or excuse me, if you have a base that is not e, it's pretty much the same, except you have to throw in a natural log of the base, which we've been doing, we just don't write it, right? If we have the derivative of e to the x, and we use this same exact formula, right, it's going to be the natural log of e times e to the x. Well, the natural log of e is 1. Okay? So, that is the more generalized rule, that the derivative with respect to x of any base to the x is the natural log of the base times b to the x. And then we can generalize it one step further with the same idea, that the derivative with respect to x of b to the rx is equal to the natural log of b times r times b to the rx. Right, we just sort of combine everything. But the one you'll see most commonly is basically with e. Right? E to the rx is r e to the rx. And specifically, the derivative of e to the x is itself, and that is the one function that has this property. Okay, so we've taken care of the exponential functions. Later on, we will look at logarithms. For right now, we're just going to focus on sort of the more basic rules. For logs, we need some more advanced tools. Next up are going to be our trig functions. Now, we can tackle the trig functions without any advanced tools, really, just with some identities and limits. So let's talk about the derivatives of our trig functions. Okay. So to build the derivatives of trig functions, we're going to build everything from sine and cosine. In fact, we can get everything from sine and cosine. But to do that, we're going to need to analyze two particular limits. Okay, so the first limit we need to look at is, is the limit as, I'm going to use theta here, but the limit as theta goes to 0 of sine of theta all over theta. And then we're going to need the limit as theta goes to 0 of cosine theta minus 1 all over theta. This might look kind of familiar as like our e to the h minus 1 all over h. That's sort of where this is coming from. Okay, eventually these will be h's, but I want to look at these a little more generally. For this one, this is of course a 0 over 0 case. Both of these are. All right, and we're going to use the squeeze theorem here for the sine theta over theta. Okay, so to employ the squeeze theorem, we need to get this between two things. And you might think, oh, we'll do, say, -1 and 1. But if we did that, like we typically do, right, sine theta is between -1 and 1, having -1 over theta and 1 over theta isn't going to help if we're looking at the limit as theta goes to 0, because this will, well, both of these are basically undefined. It's going to depend on what side you come from. Okay, so what we're going to do instead is we're going to employ our unit circle definition of sine, cosine, and tangent. Okay, now if you don't remember these, don't feel too bad about that. Okay, it's not a huge deal, but what we're going to do is put an angle theta on our unit circle. Okay, and when we do that, we make this right triangle. So, if you remember or you don't, the side adjacent is cosine theta, and the side opposite is sine theta, and the hypotenuse is 1. Okay, so I'm actually going to ruin my circle here. Let me try this instead. Put this on the inside of the circle. Okay, so we have this triangle. Then, and this is the one I think people might forget, if we extend this line out with the line tangent to the circle here, this length is actually tangent of theta. Okay, so I have essentially 3 objects that I want to compare. Okay, I have the small right triangle inside the circle. Okay, I have this arc, right, that sort of makes up the circle, and then finally we have this large triangle that goes outside of the circle. Okay. Okay, so when you think about the areas of these objects I just made, right, the area of the right triangle will be less than, okay, or equal to, really, because we're going to shrink theta down to 0, and they're going to start getting closer and closer to one another. But the idea is that this area, all right, is going to be less than or equal to the area of the pi slice. Right, so the area of the smaller triangle will be less than the area of the pi slice, which will be less than or equal to the area of the larger triangle. Okay, so the smaller triangle is a cosine by sine by 1 right triangle. Okay, the arc is, well, the pi slice has an angle theta, and the radius is 1. Okay, and then here we have a triangle with base 1 and height tangent. Okay, so the areas of these objects, well, the area of this triangle is going to be 1/2 base times height. Okay, the area of a portion of a circle, well, if you think of the area of an entire circle, it's pi r squared. If you want the portion of a circle, it's actually going to be 1/2 theta. Right, because if you take the full circle, which is, sorry, it would be theta. Okay, no, I was right. It's 1/2 theta, because typically the area of a sector like this is 1/2 theta r squared, because if you think of the full circle, if you put 2 pi in here, the 2's cancel and you just get pi r squared for the area of the entire circle, but r in this case is 1. Okay, so it just becomes 1/2 theta, and then that's going to be less than the area of this triangle, which ends up being 1/2 base times height, so just 1/2 tangent theta. Okay, now I'm going to cancel out the 1/2 on all these pieces, and then I'm going to divide through by sine. Okay, so here we'll just get cosine theta. Here we'll get theta over sine. Okay, and then here, tangent I'm going to rewrite as sine over cosine, so that when we divide by the sine, 1 over sine on this side, the sines actually cancel, and we're left with 1 over cosine. Okay, so we have cosine theta is less than or equal to theta over sine of theta, less than or equal to 1 over cosine theta. Okay? Now, we from here can flip everything over provided we flip the signs over. So I have 1 over cosine theta is less than or equal to sine theta over theta, which is less than or equal to, or sorry, greater than or equal to cosine theta. Okay? And this is going to be true for basically all thetas close to 0. Now, we can take the limit. So by the squeeze theorem, okay, we'll have the limit as theta goes to 0, 1 over cosine theta, which is greater than or equal to the limit as theta goes to 0 of sine theta over theta, which is greater than or equal to the limit as theta goes to 0 of cosine theta. And this is going to go to, well, cosine of 0 is 1. So this goes to 1 over cosine 0, so 1 over 1, which is 1. And this goes to cosine 0, which is 1. So when it's all said and done, the limit as theta goes to 0 of sine of theta over theta is 1. Okay, this is actually a very important limit. Right? It's often written as the limit as x goes to 0 of sine of x over x is 1. Okay? Now, the picture I drew was for a positive angle close to 0, but you get the same result for a negative angle next or close to 0 as well. Okay, so that's not going to really change this process. Okay? So we have this limit, it's 1. Next we need to look at this limit. The limit as theta goes to 0 of cosine theta minus 1 all over theta. Okay, so for this one it may seem strange, but we're going to use a conjugating factor. Right? I'm going to take this cosine theta minus 1 and take a cosine theta plus 1 and multiply it on the top and the bottom. And you might wonder why I would do that. I'm going to use arrows here. Well, it's because when we do our difference of squares idea to get cosine squared theta minus 1 all over theta times cosine theta plus 1, hopefully this numerator looks familiar. In fact, of all the trig identities that you should know, well, there are a few you should know, but one you should take to your grave is sine squared theta plus cosine squared theta equals 1, which means that if I move the 1 over here and the sine over there to match this, we're going to get that cosine squared theta minus 1 is equal to negative sine squared theta. Okay, so that means we could rewrite the top as a negative sine squared theta all over theta times cosine theta plus 1. Right, now I'm going to split some things up. I'm going to put the negative on the very outside. Then I have two sines here. So I'm going to take one of my sines and put it over the theta, because I know that when theta goes to 0, this piece is going to go to 1. Then I'll take the other sine and just put it over this cosine theta plus 1. Okay, so now we should just be able to evaluate our limit, because the limit of sine of theta over theta as theta goes to 0, this goes to 1, and this shouldn't cause any problems. Right, so we should have negative 1 times, now we can just plug in the 0. Sine of 0 over cosine of 0 plus 1. Sine of 0 is 0. Cosine of 0 is 1. So we'll get 0 over 2. So it's 0. Okay, so this limit goes to 0. Okay, so this limit here goes to 0. Okay, now we are going to use these two important limits to find the derivative of sine and cosine. All right, here we go. The derivative of sine is going to be the limit as h goes to 0 of sine of x plus h minus sine of x all over h. All right, and here we're going to use the sum identity for trig. All right, so we will have that this is going to end up being, will be sine of x times cosine of h plus sine of h times cosine of x. All right, if you don't remember the sum identity, that looks like 10 there. That should be a D. It's definitely something that you can look up if you don't remember. All right, and then we still have that minus sine x, and the whole thing's over h. Okay, so what I'm going to do from here is collect the sine x cases and split off the other piece here. Okay, so what we'll have is this is the limit as h goes to 0 of sine x cosine h minus sine x. Okay, and I'm going to put that all over h, and then I will have what's left here, which is sine of h times cosine x all over h. All right, and so from here, now I can factor out the sine of x, and I'll be left with cosine of h minus 1 all over h. And here I can take out the cosine x, and I'll be left with sine of h over h. And here's where we will apply the limits that we just discovered, right? As h goes to 0, cosine of h minus 1 all over h goes to 0, while sine of h over h goes to 1. Okay, so the whole thing, this is 0, whole thing is going to just cosine of x. Okay, so the derivative with respect to x of sine of x is equal to cosine. All right, that seems fitting. And it's interesting if you look on the graph why this ends up working. Right, so if we start with the graph of sine here and start looking at the tangent lines as we go forward and match the y values to the slopes that we get, okay, right, we'll notice that when we get basically a horizontal line, right, that's going to correspond to 0 for the derivative, right? And when we hit 0 for sine, its tangent line, its slope looks to be close to 1. And as we put these together, we see that, interestingly, the rate of change of sine is given to us by cosine. Now, do we have a similar idea for the derivative of cosine? Well, let's see. Okay, we'll start like we usually do. The limit as h goes to 0, okay, of, well, it will be cosine of x plus h minus cosine of x all over h. And once again, we're going to use the sum identity. For cosine, it's a little different. Okay, for cosine, it's going to be cosine x cosine h minus sine x sine h. Okay, then minus cosine of x. Once again, I'm going to join the cosine x terms together and then leave what else we have left over. So I'll have the limit as h goes to 0 of cosine x times cosine h minus cosine x all over h. And then here we'll have minus sine of x times sine of h all over h. All right, so this should hopefully look kind of familiar. We can take the cosine x out to get cosine of x, right, times the limit as h goes to 0 of cosine of h minus 1, when we factor out that x, cosine of x, all over h. And here we can move that sine x outside and be left with the limit as h goes to 0 of sine of h all over h. Okay, so as we talked about last time, this goes to 0, this goes to 1. So at the end of the day, we get a minus sine of x. All right, so yes, similar. The derivative of sine is cosine, while the derivative of cosine is negative sine. Okay, if we look at the graph, here's the graph of cosine in blue. And as we move our point around, okay, again, whenever we have like a maximum, that's when the slope is 0. Whenever cosine is 0, the slope is either 1 or negative 1. Okay, and yeah, when we trace this out, you can see it's not exactly sine, it's sine that's been flipped over, therefore it's negative sine. Okay, from here we can find every other trig function, because every other trig function is based on sine and cosine. So since tangent, right, is sine over cosine, we can use the quotient rule to find the derivative of tangent. So the derivative of tangent of x, well, that's just going to be the derivative with respect to x of sine of x over cosine of x. Okay, so using the quotient rule, would be the derivative of the top, which is cosine of x, times the bottom, which is cosine of x, minus the top left alone, just sine of x, times the derivative of the denominator, which will be negative sine of x, all over the denominator squared, so cosine squared x. Okay, simplifying the top, we'll have cosine squared x, then a negative sign times a negative sign is a plus sine squared x, all over cosine squared x. Well, sine squared plus cosine squared is going to be 1. So we have 1 over cosine squared x, also known as, well, 1 over cosine is secant, so 1 over cosine squared, well, we could write it like this. Right? This is going to be secant squared x. Okay. So there's our derivative for tangent is secant squared x. Okay, now that we have this, we can easily find, maybe I should be careful with that word easy, but we can find the derivative with respect to x of cotangent x. Because cotangent x, well, we could either say it's cosine over sine, or it's also known as 1 over tangent. And so we can use the quotient rule again. Be the derivative of the top, which will be 0, times the bottom. So that would be tangent of x left alone, minus the top left alone, times the derivative of the bottom. Well, the derivative of the bottom, we know now, is secant squared of x, all over the denominator squared, which is tangent squared x. Okay, so this comes out to be, well, that just zeroes out, and we'll get negative secant squared x over tangent squared x. But there's a much nicer way to think about this if we split up this fraction. This is negative secant squared times the 1 over tangent squared will be cotangent squared. All right, so we'll get 1 over, so secant squared is cosine squared x, so, or 1 over that. Then cotangent squared, which will be cosine squared x over sine squared x. Okay, so the cosine squareds cancel, and we are left with negative 1 over sine squared x, which will be negative cosecant squared x. Okay, so the derivative of tangent is secant squared x. The derivative of cotangent is negative cosecant squared x. Okay. Now if we compare these rules that we just found, notice that derivative of sine is cosine, the derivative of cosine is negative sine. Derivative of tangent is secant squared, but the derivative of cotangent is negative cosecant squared. This pattern is actually going to hold where whatever the pattern is for the normal trig function, the co-function adds in a negative and uses the other version of the similar trig function. So instead of, like, sine goes to cosine, but cosine is negative sine. Tangent gives us secant squared, but cotangent throws in a negative and makes it a cosecant squared. This pattern is going to hold for the next two trig functions as well. So let's take a look at. All right, so to find the derivative of secant, what we're going to do instead is find the derivative of 1 over cosine, which we'll use the quotient rule for. So it will be the derivative of the top, which is 0, times the bottom left alone, minus the top left alone, times the derivative of the denominator, which will be negative sine of x, all over cosine squared x. Okay, so this ends up being, well, that negative negative gives us a sine of x, all over cosine squared x. Okay, so to simplify this, what we're going to do is break it up so that I have sine of x over cosine of x times 1 over cosine of x. And the reason we do that is so that we can rewrite this as, well, sine over cosine is tangent, and 1 over cosine is secant. Okay, so the derivative of secant is tangent x, secant x. Okay, so I often write it like this. The derivative of secant of x is secant x tangent x. It doesn't really matter what order you write it in since it's multiplication. Okay, but similarly, if we go through this process again but with cosecant, what you'll find is that the derivative of cosecant is negative cosecant x cotangent x, right? The same pattern, just with a negative and the co-functions instead, right? If secant goes to secant tangent, cosecant goes to a negative cosecant cotangent. It's the same pattern, just with the co-functions and negative. Okay, so here we are on one full screen. All of our trig function derivatives for sine, cosine, tangent, cotangent, secant, and cosecant. Here's my advice though. If you remember just sine, tangent, and secant, or really, if you just remember sine, cosine, you can get all the others. I have had some students in the past that will just always use the quotient rule every time they need to do this. I don't recommend that, but you can. However, if you know sine and cosine, you should know those pretty well, but if you know tangent and secant, then you know cotangent and cosecant, because all you do with cotangent and cosecant is take the same pattern, but make it negative and make it a co-function. Right? If tangent goes to secant squared, then cotangent goes to negative cosecant squared. Secant goes to secant tangent, cosecant goes to negative cosecant cotangent. Okay? If sine goes to cosine, then cosine goes to negative sine. Okay? So these are all the derivative rules that we consider the basic rules. And we'll talk about in the next actual lesson why that is. Okay? And what we mean by that. So these are all the rules. I'm going to stop here. Now, while I do think you probably do have enough information to get rolling on the homework, I am going to put a lesson after this one, or a video after this one, before we truly move on to the next lesson, where I just do a bunch of examples. All right, so if you feel like you've got enough to move on, go right ahead. Otherwise, stay tuned for the next video, where it will literally, since we've done all this stuff and gotten it out of the way, it will literally just be examples of derivative rules from product rule, quotient rule, to trig, exponentials, all of that jazz. Okay, so I'll catch you all on the next one. Cheers.